Here we are in Topic 2, One-Dimensional Kinematics of the first year algebra-based physics course. In Section 2.9, I will be discussing how to determine the meaning of the slope of and the area under a line on a graph. So what do we mean by the slope of a line on a graph? Well, think of the slope as the slope on a mountain. Right? If you have a very steep mountain that's very hard to climb, all right, then the slope, all right, again, is very steep. All right, that's a high slope. It's a big number. All right, it's hard to climb. Now, if you just have a hill, all right, a hill like this, and you want to run up the hill, well, that slope is very gradual or gentle. It's a low number. All right, there's a gradual or gentle slope. So if I now move the slopes from my mountain and my hill to the graph, this slope would be considered steep, a steep slope. That's going to be a large number. Now, this slope here would be a gradual or gentle slope. A gradual or gentle slope. And this would be a small number. Now, of course, these two slopes, the numbers would be relative to each other. This number could be 2, and this number could be 0.4. All right, it doesn't really matter. The bottom line is that this slope would have to have a larger number than this slope. Now, you should also be able to recognize the difference between a positive slope and a negative slope. All right, a positive slope and a negative slope. Positive slope, negative slope. All right, now I won't talk a lot about curves today, all right, probably just right now. And also keep in mind that the terms line and curve are often used interchangeably. When people are talking about a graph, they might call this a line or a curve. They might call this, all right, a line or a curve. All right, so the two terms are used somewhat interchangeably, all right, but when the line is actually curving, okay, let's talk about that a little bit. Okay, so, all right, here we have a graph. It's exponential, all right, it's curving. Okay, now, to find the slope on a curve at any given point, now keep in mind, on a curve like this or this, the slope is changing. This is not a constant slope, neither is this. All right, now if I were to draw the slope here, all right, tangent to the curve, this would be a very gradual slope. And what's happening is as this curve is going up, right, the slope is increasing. The slope is going from here to here to here. This slope is increasing, all right, on this graph. All right, now over here, again, you draw the slope tangent to the curve, all right, and that means it's going to look like this. So here, all right, the slope would be something like this at that point, something like this at that point, and something like this over here. So this slope, all right, is decreasing. Okay, this slope is steep, then more gradual, and then even more gradual. All right, so this is an increasing slope. This is showing a decreasing slope. All right, and like I said, I'm not going to go too much more into actual curves during this video, but I did think this little bit here is important that you know. All right, now before you start trying to interpret a graph, you want to absolutely train yourself to look really carefully at the title of the graph and the labels on the axes. Right? This is going to be critically important to the interpretation of what the graph is telling you, what the graph means, what the slope means, what the area means, etc. Now, on this graph here, on the y-axis, I'm going to label that displacement. All right, displacement. So that is the physical quantity that we're putting on the y-axis. Now, the unit for displacement, of course, is meters. All right, so every axis is going to have two things. It's going to have a physical quantity and a unit for that physical quantity. Keep in mind that many teachers and many questions on various physics tests will get you no points whatsoever if you forget about the unit on the axis, all right, or if you put the wrong unit. All right, so definitely take a look at the physical quantity, all right, that's being shown, and the unit for that physical quantity. On the x-axis here, I'm going to put the physical quantity time. And of course, the unit for time is seconds. Now, the convention for the title for a graph, the simplest title you can possibly put on a graph, would be y versus x. In other words, for this graph, it would be displacement, which is y, versus time, which is x. So the simplest title that we could put on this graph would be displacement versus time. All right, now we could put more in the title, but that's the least that you're going to put in a title in general for a graph in physics. All right? And so again, you could have many, generally speaking, in the beginning of the physics course, a lot of the graphs will have time on the x-axis. So you especially want to take note of the y-axis. All right, another common physical quantity for the y-axis might be velocity. All right, and of course the unit for velocity, meters per second. All right, so you want to, before you start trying to do a problem that involves a graph, you want to absolutely take a look at the labels on the x and y axis, all right, and take a look at the title of the graph. All right? All right, so how do we calculate an exact number for the slope of a line? Well, we've got two lines on this graph. Now, this is a displacement versus time graph. Here's the unit meters for displacement. And again, this is a displacement versus time graph. All right, displacement versus time. All right, now, you notice we have a steep slope here. All right, the blue slope is very steep. It is going to be a larger number. When we calculate the slope of the blue line will be a bigger number than the slope of the red line. The red line is a gradual, right, or gentle slope. And this number, when we calculate it, will be smaller. All right, so this number will be bigger, this number will be smaller. You know that before you even start. This is a gradual slope. This, right, is a much steeper slope. All right, now I'm going to get rid of those words so that we don't have too much, right, on this graph. We don't want this graph to be a mess. All right, so let's get rid of that now. All right, so your first step, and let's calculate the slope of the red line first. All right, let's calculate the slope of the red line first. Your first step is to select 2 points on the line. Now, select 2 points that are easy to read. I like here, all right, how about, all right, now this is x, comma, y. So this is going to be 8 seconds, comma, 4 meters. All right, now this is actually, x2, y2, because I'm going to select my second dot down here, and this dot, all right, is 4 seconds, comma, 2 meters. Okay, and this would be x1, y1. All right, so starting from 0, the first dot that you come to is x1, y1. The second dot that you come to is x2, y2. All right, now, the equation for the slope of a line. All right, the slope of a line is the change in y over the change in x. All right, so that's going to be y2 minus y1 divided by x2 minus x1. So we're going to start plugging in now. All right, now, I will also say that if you want to use 0, 0 as your x1, y1, of course, that makes things much, much easier. All right, but I'm going to do a slightly more, I don't want to say complicated problem. It's not difficult by any means, but I'm not going to use 0, 0 for x1, y1, just to show you a more sophisticated problem. But absolutely, if you want to use 0, 0 for x1, y1, that would make this equation much more simple. All right, so here we go. y2 minus y1, all right, 4 meters minus 2 meters, over x2 minus x1, 8 seconds minus 4 seconds. Now, notice that you must put the units into the equation. It is super, super important in physics that you always, always, always put the units. All right, most physics teachers will not give you any credit for a problem if you put the wrong units or if you leave the units out. All right, so what do we have here? We have 4 meters minus 2 meters, so that's 2 meters on top. 8 seconds minus 4 seconds, that's 4 seconds on the bottom. 2 divided by 4 is 0.5, and the correct unit here, meters per second. Remember, when you see a division sign, all right, you say per. So the correct unit is meters per second. All right, so you find, since the unit is meters per second, you find that what you have calculated here is a velocity. All right, so you can say the slope, all right, or the velocity is, you could put a 0 in front if you like, 0.5 meters per second. All right, so the slope of the red line is a 0.5 meter per second. All right, now I'm going to erase this, all right, and we're going to calculate the slope of the blue line. And I tell you what, before we do that, let me just show you what I was talking about using 0, 0 for x1, y1. All right, if you use 0, 0 for x1, y1, if your graph, if your line goes through 0, 0, you could use x1, y1, all right, 0, 0. So this x would go away, this y would go away, and the only thing you would have to do is put y2 divided by x2. So that would be, all right, 4 meters, y2, divided by 8 seconds, x2, and you're still, of course, going to get the right answer, 0.5 meters per second. All right, so using 0, 0 as your x1, y1 does make the problem a little bit quicker and easier. All right? Okay, now let's calculate the slope of the blue line. All right, so we're going to pick two points on the blue line. All right, I think I'm going to pick, all right, 4, 8. All right, so 4 seconds, right, 8 meters. And then at 2 seconds, all right, that would be 2 seconds, 4 meters. All right, so this would be x2, y2. Down here would be x1, y1. And again, there's no reason why you couldn't use 0, 0 for x1, y1. All right, so the slope of the blue line is the change in y over the change in x. It's y2 minus y1 over x2 minus x1. All right? So y2 is 8 meters. y1 is 4 meters. And please note that I label x2, y2, x1, y1. It is so easy to mess up the x's, the y's. Is it the 1? Is it the 2? It's such a common mistake. I like to label the x1 and the y1 and the x2 and the y2 to make absolutely certain that I'm not going to screw up this very easy problem. All right. x2, all right, is 4 seconds minus x1 is 2 seconds. All right, so on top we have 8 meters minus 4 meters, so we have 4 meters on top. On the bottom, 4 seconds minus 2 seconds, we have 2 seconds on the bottom. So your final answer, 4 divided by 2, all right, is 2 meters per second. All right, and again, since it's meters per second, you know that what we just calculated was a velocity. All right, so the slope, all right, or the velocity for this graph is 2 meters per second. All right, now, I mean, technically, we only have one significant figure here, so I really should not be putting these point zeros here. All right, I'd like to put 0.0 or 0.00, but there just isn't enough room on these graphs and on the paper. The graph is much neater if I just put one significant figure. So that's the only reason why I'm hesitating to put more than one significant figure. All right, so what you find is that the slope of this red line, right down here, right, the slope of the red line, let me just erase some of this extra stuff here that we don't need anymore. All right, the slope of the red line was 0.5 meters per second. The slope of the blue line was 2 meters per second. So as we said at the beginning, this is the steeper slope, so it will be the larger of the two numbers. This is the gradual slope, right? It will be the smaller of the two numbers. The number 2 is bigger than the number 0.5, right? A slope like this is always going to be a bigger number than a slope like that. All right? Now, just a little bit about what the slope is actually showing. All right? Okay, so what the slope is actually showing is that every time we go over 1, all right, this slope goes up a half. All right, so it's a half a meter every second. All right, so if you look, we go over 1 second, we go up a half a meter. So by the time we get to 2 seconds, we've gone up to 1 meter because we've gone up another half a meter. Every time we go over 1, we go up a half. Over 1, up a half. Over 1, up a half. Now, the reason the blue slope is steeper is because the slope is 2 meters every second. So when we go over 1 second, we've already gone up 2 meters. When we go over another second, we've gone up another 2 meters. We're up to 4 meters. This slope is going up much quicker than this slope is going up. So again, you're going over for the x and then up for the y. Right? Over for the x, up for the y. If you're going up half a meter every second, you're not getting up very quickly. You've got a gradual slope. If you're going up 2 meters every second, you're going up much faster and you've got a much steeper slope. All right, so we've calculated the slope of this line and we've calculated the slope of this line. We found that this number is greater, so this slope is greater. We found that the units tell us that we've just calculated the velocity. So this person here, this blue person, is obviously running faster or walking faster than the red person, right? If the blue person's velocity is 2 meters per second and the red person's velocity is half a meter per second, then this person, right, this person here right, is faster, right, and this person here is slower. Okay, so we got a lot going on here. You can tell a lot from a graph in physics. All right, so what do we mean by the area below a line or curve on a graph? Now, the graphs here don't go up quite as high as the graph on your worksheet, but it's not going to be a problem for our calculations. All right, so let's say that this person is moving at a constant velocity of 3 meters per second. All right, so the y-axis is velocity, and this person stays at 3 meters per second, 3 meters per second, 3 meters per second, 3 meters per second. This person is not speeding up, not slowing down. He or she is walking at a constant velocity of 3 meters per second. And let's say we want to know how far the person goes in 4 seconds. All right, so I'm going to mark off 4 seconds right here. All right, and since the interval we're looking at is 4 seconds, I'm going to fill in the area under the line for the first 4 seconds. So here's the area that we're talking about. All right, right there. Now, for the second graph, all right, this person is actually accelerating. They're probably in a car. All right. Now, this person is accelerating. All right, and this graph at 4, the person is at the 8 location. All right, so we'll put that right there. All right, so here's the graph for the second person. And again, they're probably in a car. All right, so here we go. This is our second graph. Now you notice this graph is not a flat line. Right? This graph is a diagonal. And let's ask the same question. Right? How far has this person gone in the first 4 seconds? All right, so we're going to draw a line straight down, right, at the 4-second mark. And the area under that line is what we're going to calculate. So we're going to calculate this area here. All right, that's the area that we're going to calculate. All right, so notice that this area is a rectangle. This area is a triangle. So you're going to need the equation for the area of a rectangle here. Perhaps you remember that the area, all right, of a rectangle, I'll put that right there like that, is the base times the height. Here's the base, 4. Here's the height, 3. Now the area of a triangle, all right, the area of a triangle is going to be half the base times the height. So it's going to be half of the base, which is 4, times the height, which is 8. All right, so I'm going to erase these, and we're going to come back. We're going to calculate this area first, then we'll calculate this area, and we'll try to figure out what those areas mean. In other words, what do these areas have to do with physics, with actual people running or driving cars or whatever? All right, so here we have the same graph. This time we did get all the way up to 10, all right? But we're focused on a person moving at 3 meters per second, a constant speed or velocity of 3 meters per second. 3 meters per second, see, this is the velocity. 3 meters per second, 3 meters per second, 3 meters per second, 3 meters per second. The velocity is not changing. This is a constant velocity. We'd like to know how far the person travels in 4 seconds. All right, so at 4 seconds here, all right, we're going to draw a line. So what we want is the area under the line, all right, at the 3 meter per second velocity and the 4 second, all right, mark. So we're going to calculate that area. All right, it's actually a rectangle because it's 4 and 3. All right, the scales aren't exactly the same, but it is 4 by 3. So it's actually a rectangle. All right, so here we go. All right, the area, all right, of a rectangle is going to be equal to the base times the height. Now, again, in physics, when you put the numbers in for base and height, you have to include the units. So the base is 4 seconds, all right, 4 seconds, and the height, right, 3 here, is 3 meters per second. The height is 3 meters per second. Now keep in mind, this second here is actually seconds, but of course it's over 1. All right, so seconds and seconds are going to cancel. 4 times 3 is 12. The only unit we have left, the seconds canceled, the only unit we have left is meters. So the area of this rectangle under the line on the graph is telling us the displacement. The unit we have left here is meters. All right, so that is telling us that what we just calculated was the displacement. All right, and the displacement is 12 meters. Okay, so we figured out that the area under the line of a velocity time graph tells you the displacement. Now we're going to talk more a little later about why that is. All right, but for now we can accept that since the unit came out to meters, it must be displacement. If this is velocity, then this must be displacement. All right, and the unit also tells us that it's displacement. Now here we have that same blue line, all right, the second graph that we just looked at before, and we've gone up to 10 this time, all right, and we'd like to know, all right, this person, let's say that they're starting a car from rest, the velocity at the beginning is 0, and this person is going to see the velocity is increasing, velocity, so this person is going faster and faster and faster and faster. We'd like to know how far this person has traveled in the car or on the horse, whatever, in the first 4 seconds. All right, so here's 4 seconds. All right, so we make a line up from the 4 seconds. All right, and that line hits right here at 8. All right, so at 4 seconds, the velocity is 8 meters per second. And we are trying to find this area. All right, the area between 0 and 4 seconds. So right there, this is the area that we're trying to find. And you notice right away that this area forms a triangle, not a square, not a rectangle. This area, okay, it could be a little straighter there, but this area forms a triangle. So to calculate this area, we need the formula for the area of a triangle. All right, the area, all right, of a triangle is going to be 1/2 the base times the height. So here we go. All right, the base is 4 seconds. Now I will mention one other thing in just a minute, I guess. The height, all right, is 8 meters per second. All right, 8 meters per second. And I'll mention this now. If you say you're going to put the base first and then the height, make sure that the 4 is here, the base, and the 8 is here for the height. Technically, if you were to switch them, your math would not be quite as elegant. It would be wrong, okay? I mean, it's not going to matter once you multiply all the numbers, but from a technical standpoint, all right, if you say you're going to put the base here, that's 4, the height here, that's 8, don't switch them, okay? So be a little bit careful about that. All right, now, 4 times 8 is 32. Half of that is 16. So this is 16, all right, and again, this S is really S over 1. It's S over 1. All right, the 4, I mean, technically the S and the 4 are both over 1. It doesn't really matter. All right, everything is over 1. All right, so the S on top and the S on the bottom cancel. All right, and 4 times 8 is 32. All right, the 8 is really over 1 also, it doesn't matter. 4 times 8 is 32, and half of that is 16. So this is 16, and the only unit we have left, and the answer is meters. 16 meters. That's how far this person went. If they started from rest, their initial velocity was 0. They drove for 4 seconds at a certain acceleration, and their final velocity was 8 meters per second 4 seconds later. They have traveled a total displacement of 16 meters. All right, so the displacement is 16 meters. Now, we haven't said what direction. All right, we're only getting the magnitudes here. We have not mentioned what direction this person is traveling. Technically, to be a displacement, you need to know the direction. All right, but we'll get into that in a different video. Now, before we start this problem, I want to make sure that you understand one thing about the unit for acceleration. All right, the unit for acceleration is meters per second squared. But what does that really mean? It's really meters per second per second. Let me put that over here. All right, so if your acceleration is 2 meters per second, all right, and again, that's 2 meters per second squared. What that means is that every second, your speed is increasing by 2 meters per second. All right, so if you start at a speed of 0, after 1 second, your speed has gone up 2, so now your speed is 2 meters per second. If you go for another second, your speed goes up another 2 meters per second. So now your final speed is now 4 meters per second. Every second, your speed goes up 2 meters per second. Now, the reason I'm emphasizing that right now is because if you understand that, then it's very, very simple to graph this question on this graph. Let's do that now. All right, so what is this person doing? All right, and maybe we'll use green. I hope the green is working. Yeah, the green's pretty good. Okay, so a man in a car is traveling at a velocity of 2 meters per second for 3 seconds. So here's my velocity graph. He's from the beginning of the problem, he's at 2 meters per second. And he does that for the first 3 seconds. So 2 meters per second, see the velocity? All right, for 3 seconds. 1, 2, 3. All right, so that's the beginning of the graph. It's a flat line. All right, now, after that, after the 3 seconds, he starts to accelerate at a rate of 2 meters per second every second. That's 2 meters per second squared. This is the same thing. All right, now, for the next 3 seconds. So, at 4, he's accelerated another 2 meters per second. So instead of 2, his velocity is now 4. So we'll put it right there. After 1 second, his velocity has gone up 2 meters per second. So his velocity is now 4. After another second, his velocity is up to 6. So right here, his velocity is up to 6. That's a little too high. Maybe right about there. All right. Now, after 1 more second, his velocity is up another 2 meters per second. So we're right about there. Okay? Now this is my first 3 seconds. This is my next 3 seconds. So my total time is 6 seconds. So I'm going to go up right there. That's the total time that this little story is happening. All right? And the other thing that I'm going to do is draw this diagonal. It's a straight line, but it's diagonal. Okay, right there. Okay? Now, what we want to know is what is the magnitude, just the number, of the total displacement during the 6 seconds. So we need, all right, from the beginning here to here, from here to here, we need this entire area. Now, what you've got here, you've got a rectangle here. All right, you've got, let's see, that's 3 by 2. You got another rectangle, and you've got this triangle. All right, so for the entire 6 seconds, you're going to have to add up this rectangle plus this rectangle plus this triangle. Actually, we could break it into two rectangles, all right? We could do this rectangle, all right? That's going to be quicker. This rectangle, right? That whole rectangle plus this triangle. Okay? So let's do that. And we can do that fairly quickly, all right? This doesn't have to be a complicated endeavor here. All right. So you see how understanding the meaning of the unit for acceleration, meters per second, meters per second squared, allowed us to draw the graph very, very quickly and easily. Now, I'm a little too high here, all right, but that we can deal with that. All right, so first we need the area of this rectangle. All right, so the area of the rectangle is the base times the height. The base is 6 seconds. The height of that rectangle is 2 meters per second. All right, so what we've got here is 12 meters. The triangle, okay, the area of the triangle is half the base times the height, so half. Now the base of the triangle is from here to here, so it's from 3 to 6. So the base of the triangle is 3 seconds. All right, and the height of the triangle is from 2 to 8. So the height of the triangle is 6 meters per second. All right, so the height of this triangle is half of 18 or 9 meters. All right, so the total displacement is going to be 12 plus 9. All right, so we've got 21 meters. All right, is the displacement for the entire 6 seconds. Now, while we're at it, what if we just wanted the displacement from 3 seconds to 6 seconds? All right, from here, all right, to here. So that would include this box here plus the triangle. Well, we've already got the triangle. The triangle is 9 meters. So let's just get this box, all right, which actually I believe is going to be half of this box. I think it's going to be 6, but we'll do it, all right? So let me just move this over a little bit. All right, D equals 21 meters. All right, so this box here, all right, so we'll call this area rectangle, all right, 3 seconds to 6 seconds is the base times the height. All right, so in other words, from 3 seconds to 6 seconds, how far did he go? All right, it's this triangle, right? That's part of the 3 to 6 seconds, but we need this box here also. The base of the box from 3 to 6 is 3 seconds. The height of the box from 0 to 2 is 2 meters per second. So yes, we've got another 6 meters. All right, so that displacement, right, from 3 seconds to 6 seconds, right, that displacement is 9 plus 6, or 15 meters. Okay, so there's a lot that you can do here. All right, and one of the keys is when you have a graph, you want to try to look for rectangles, squares, and triangles, all right, under the lines on the graph, under the lines on the graph. So just a quick little recap here before we move on. What we found out so far is that the slope of a displacement versus time graph is giving you the velocity. Now, a greater slope than the blue line would be a faster velocity, and a more gradual slope, like the red line, would be a slower velocity. But here's the question. What about the area under the line on a displacement time graph? Does the area under the line on a displacement time graph mean anything? In other words, if I were to calculate for this amount of time the area of this triangle, would that tell me any useful information? Now here we had a velocity versus time graph, and what we discovered is that the area under a velocity versus time graph tells you the displacement. This area is how far the person went, in that amount of time, or how far the object traveled in that amount of time. But what about the slope of a velocity versus time graph? Does the slope of a velocity versus time graph tell you anything? For example, the slope here is 0. So what I'll be doing from this point forward is talking about an easy way to figure out the meaning of the slope of any graph, no matter what it says on the axes, and an easy way to figure out the meaning of the area under the line for any graph, no matter what it says on the axes. And again, see that there are different meanings based upon the labels on the axes. Remember, at the beginning of this video, the very first thing that we did was discuss how important it is to look carefully at the labels and the units on the axes before you start trying to interpret or answer questions about any graph in physics. What I'm going to talk about now is how to determine the meaning of the slope of a line on a graph, and then how to determine the meaning of the area under the line. Let's start with the slope first. Now, you know how to calculate the slope. We've done that already, and you've done that in other classes, like your math class, for example. To calculate the slope, you do change in y over change in x. Well, if you want to know what that slope means, you're still going to divide y by x. So, for example, on a displacement time graph, you can divide the d divided by the t, and you'll recognize right away that dividing d by t, y divided by x, is an equation for velocity. So you can take the d, the physical quantity, d, and divide it by t. You can also get a hint about the meaning of the slope by dividing the units. What if you divide the meters by the seconds? All right, we know that meters divided by seconds is the unit for velocity. So again, whether you're looking at d divided by t or you're looking at meters divided by seconds, both of those divisions are telling you that this slope is going to be a velocity. All right, let's look at a different graph. Here's a velocity versus time graph. What is the meaning of the slope of this line? See, it's a different graph. All right, this is a displacement time graph. This is a velocity time graph. The slope of the line means something different. So again, you can take the physical quantity, velocity, and divide it by the physical quantity, time. And you'll probably recognize that that is the equation for acceleration. Go to your Regents Physics reference tables and look on the last page, the mechanics page. All right, the equation for acceleration is change in velocity over change in time. We'll just put t, we'll imagine that t1 is 0. All right, so again, anytime velocity is divided by time, all right, that's giving you an acceleration. So if you calculate the slope of this line, you're getting the acceleration. All right, now, the other thing you could do is put the units, all right, divide the units. So on the top it would be meters per second, all right, meters per second, divided by the unit for time, which is seconds. And perhaps you recognize, again, that this is the unit meters per second squared. So again, both the physical quantities divided, y divided by x, and the units divided, meters per second divided by seconds, are telling you that the meaning of the slope of this line on this graph is the acceleration of that object. What about figuring out the meaning of the area under a line or curve on a graph? Now, for the curve, of course, you're going to need calculus. We won't be going into that for an actual curve. But for lines, it's easy. We can do it with basic algebra and geometry. All right, so how to determine the meaning of the area under the line. Now, for the area, we know that what we did before to actually get the number was to multiply basically the x value times the y value. So y times x, x times y, all right? You're getting the area under the curve. So to figure out the meaning of that area, you can take the physical quantity displacement times time and multiply them together. Now, you look at displacement and time and you say to yourself, well, the equation that comes to mind, which might give me a hint as to what displacement times time might mean, is the equation v equals d over t. Now, we can rearrange that equation to try to see if at any time displacement is multiplied by time and if it means anything. Well, velocity is displacement divided by time, so clearly these do not match. Now, if I cross multiply, then I find that d times 1 equals v times t. All right, well, I still don't have displacement times time. This is velocity times time. All right, and velocity times time would be displacement, but again, I don't have displacement times time. Now, what about velocity and time? Since they're inversely related, you can switch the inversions. Just switch, put the t up there, put the v down there. So let's do that. And what we get is the equation t equals d over v. Now, all three of these are valid equations. If you take the displacement, divide by the time, you get the velocity. If you take the velocity, multiply by the time, you get the displacement. Take the displacement, divide by the velocity, you get the time. But no version of this correct equation gives me displacement times time. All right, basically, I am coming to the conclusion that displacement times time has no meaning. All right, there is no physical meaning for taking the displacement and multiplying it by the time. Now, if you use the units, all right, meter and second, and multiply those instead, you get a meter second. But what's a meter second? There's no such thing as a meter second. Now, I do understand that there is a millisecond, but that's not what this is. This is meters. All right, a millisecond. All right, if this was a different problem, all right, and we were discussing milliseconds, then this would be a single correct unit. All right, but as a meter second, all right, in the context of this problem, there is no such unit as a meter second. So again, the area under this particular graph right here, this area here, has no physical meaning. All right, no physical meaning. All right, now let's look at the velocity time graph and see what the area, use the same format to figure out the meaning of the area under a velocity time graphs line. So here we have a velocity versus time graph, and we're asking the same question. How can we easily figure out the meaning of the area under this line? All right, so let's take a certain amount of time, all right, whatever this is, 1, 2, 3, 4 maybe it's 4 seconds, whatever this is. It could be 1,000 seconds. And let's fill in the area here up to this amount of time. We want to know the meaning of that area. So we take the physical quantity velocity and multiply it by the physical quantity time right here. All right, now we see velocity and time. Right away, this equation comes to mind, v equals d over t. But you see that this does not match this. All right, this is displacement divided by time. It's not showing velocity times time. So let's rearrange that equation. Let's put the v over 1 and cross multiply. D times 1, all right, equals v times t. All right, and oh, look at that. Okay, so velocity times time means displacement. All right, the meaning of the area under this curve is the displacement. All right, you figure out the area of this triangle. That's how far the object or the person traveled in that amount of time. All right, now, use the units. You get the same answer. All right, the unit for velocity is meters per second. The unit for time is seconds. Now this second is really seconds over 1. All right, it's really s over 1. So the seconds are going to cancel, and oh, look at that. The unit is meter. Well, of course the unit is meter. If it's displacement, the unit has to be meter. All right, so everything checks out. Now, I mean, just for the heck of it, let me also switch these two. All right, T equals D over V. All right, the three versions of this equation, the one that applies is this one. All right, this does not apply, this does not apply. We wanted an equation with velocity times time, and we found that that equals displacement. The units agree with the physical quantities. Now, see how easy this is? Let's try some other labels on the axes and apply these same technique, all right, to some different graphs. Some graphs that you probably haven't seen yet. Maybe some graphs in the work energy power topic, or maybe some graphs in the electricity topic. All right, now watch how quickly you can figure out the meaning of the slope and the area of any graph. Let's go over the displacement and velocity graphs again, and then introduce a new graph. All right, force, the unit of which is the Newton, times displacement. Right, with displacement on the x-axis, the unit of which is meters. All right, so let's do this. Okay, to figure out the slope, d divided by t, right, and we know that d divided by t is going to give us v, so the meaning of this slope is the velocity. All right, here the area, d times t, all right, that has no meaning. All right, there is no equation where displacement is multiplied by time. All right, d times t has no meaning. All right, here, velocity divided by time. All right, let's say change in velocity divided by time gives us the equation for acceleration. All right, so the meaning of the slope of this graph is acceleration. All right, and if we take v times t, we know that v times t is displacement. Now you can just look on your reference tables to remind yourself of all these little equations. You'll start to memorize them after you've been using them for a couple of weeks. All right, so here, the meaning of the area is the displacement. Displacement. All right, now, this one here, perhaps you've never seen this before. This is the force, the unit is newtons. This is displacement, the unit is meters. All right, so if we want to figure out if the slope of this graph means anything, it would be force divided by distance. You go onto your reference tables, you don't see an equation where force is divided by displacement. All right, so we're going to say that this has no meaning. All right, the slope of this graph does not have a meaning. All right, but if you take the area, all right, force times distance, you see on your reference tables that work is force times distance. So if you take the area here, all right, let's say there's the time that you've been asked to look up to, all right, if you take the area, that's going to tell you the amount of work that was done on an object. All right, so again, very, very quickly, for slope, you divide y divided by x. You can either use the physical quantities or the units. All right, they're both going to give you the same answer. And for area, you multiply y times x, x times y, whatever. All right, and that's going to give you the meaning of the area of under the line of that graph. So here we have some graphs that apply to the electricity topic. You might not be up to that topic yet, but the same techniques apply. So when you get up to that topic, you will apply the same techniques. Let's take a look. All right, we have here a graph of charge versus time. The symbol for charge is Q. All right, so the slope of this graph, Q divided by T, if you look on your reference tables on the electricity page, you'll see that charge divided by time gives you the current. So the meaning of the slope of this line is current. All right, charge times time has no meaning. All right, you will not find an equation where charge is multiplied by time. All right, here, voltage and current. Voltage divided by current gives you R for resistance. So the meaning of the slope of this graph, this line, is the resistance. If you calculate that slope, that is the resistance for this problem. Now, I times V, you'll find, gives you power. All right, so the area under this curve is going to give you the power. So this is resistance, all right, and this one down here gives you the power. What's very interesting is that sometimes both the slope and the area have meaning. Sometimes only the slope has meaning, such as this case here, all right, that's current. And sometimes only the area has meaning. All right, let's look at this one. All right, I over R, all right, there is no I over R, all right, so this one has no meaning, all right, we'll just put an X there, all right, this one has no meaning, we'll write that there, no meaning, okay, and this one is I times R, that would be voltage. And again, you can find this equation, this equation, this equation, this equation easily on any physics website, all right, or the physics reference tables, the New York State Regents Physics reference tables. So this would be the voltage, all right? So again, this whole video has been an introduction to graphs and the meaning of slopes and the areas under the graphs, and how to find them, all right? And keep in mind, if you're talking about, you want to know what the slope means, you're going to divide. It's going to be y divided by x. You can divide either the physical quantities, or you could divide the units, all right? And you're going to figure out that the units tell you exactly the same thing that the physical quantities tell you. If you're trying to find the area, you're going to multiply. So to find the slope, you divide y divided by x. To find the meaning of the area, you multiply y times x times y, same difference. See you in the next video.